Welcome to another podcast. In this episode, we're going to be taking a look at how to calculate the work done by variable force. Now, the word variable force here is key because you're probably all familiar with from high school physics classes or even college physics classes the concept of work in general, and that is work is equal to force times distance. And while that is true, that is only true when the force is constant. So that's somewhat limiting because there are lots of scenarios, as we'll see in this video, where force is not always going to be constant. An example of constant force would be on a flat surface. You have some sort of object that has a certain mass, and you're applying a constant force to move that object from a point A to B. Then the total work done on that interval would be the force applied times the distance. It would be F of V minus A. And really where that comes from, and this is what we want to get across in this video, is if you think of force as being a function, then what we're looking at for this particular case would be a force, a constant force F applied over the interval from A to B, in which case the area under that curve would represent the work. So one thing that we may want to do to interpret work here is interpret work as the same thing as the area under a force curve, which means that work is defined in terms of the integral of force, and that's the most basic definition we're going to start with. Work is the integral from A to B of some force f of x dx. Now, what's an example where we might have a variable force? Well, an example of a variable force might be something like this. So suppose I had this as my function. And so let's just call this the curve y equals, let's say 1/2 x. Then describe what's happening there. You start off with the object at 0, so you're at location 0. And as you start to move the object, it becomes increasingly harder. You have to apply a larger force to be able to move the object. Now, I'm not moving the object, so just make sure that we're clear on this. I am not moving the object up this incline. This graph is simply the graph of the force it takes to move the object. So what is the scenario or the picture that this paints? This would be like describing stretching a spring, let's say. The reason it's like stretching a spring is if you think about what a spring does, a spring has sort of a natural length, which we would call the equilibrium. So this is sort of its equilibrium length. So this is where it would be when it's just hanging there. And then if I attached a weight on the end of it, it would then stretch it, and we're looking at it stretching it all the way up to the point D. So this is level D. So we've displaced it by d meters, d feet, whatever. And the point is, the further you try to stretch the spring away from where it wants to be, the harder it is to do that. It doesn't actually get easier the further you get away from a spring. If it did get easier, then that would be a different force curve. But that would be sort of an odd situation to be in. But that's one example where the force is not constant. In other words, moving from 0 to 1 requires less effort than moving from 1 to 2 and so on. And so the work that's involved would be calculated as the integral under that curve, under that force curve. So this is the force involved in this particular case. So there are essentially three types of work problems that we're going to pursue. We've just talked about one, and that is problems that involve springs or spring-like motion. With springs, the force is always proportional to the displacement. So remember that the x variable here for a spring problem is the spring's displacement from equilibrium. So whatever its natural length is, x represents the displacement from that. And it gets proportionally harder as you displace the spring from equilibrium. This is called Hooke's law. You've no doubt probably run into this in a physics class or two if you've taken those. So that's one type of problem that has a variable force. Another type of problem that has a variable force are what are called lifting problems. A lifting problem is, we basically think of work as being force times distance. But if I'm lifting an object, then the force required to lift an object of mass m is to overcome the gravity g, the gravitational constant g, holding it down. And so m times g would represent the weight of the object, and weight of objects is the force required to move them. And so our formula there would become m times g times the distance. But then we can further iterate on this. If this is a three-dimensional object, then the mass of the object is its density times its volume. And so I'm looking at density times volume times gravity times distance. All of that is describing the work done in this case. And it turns out that, when you do the force here, we all know that force is mass times acceleration. So that's where the mg part comes from. But the point is, if I want to describe the work, I can end up describing it as the integral of this force term, which just got a lot more complicated. The force term is now rho, the density, times the gravitational constant, times the volume. And the volume is composed of two pieces. It's the area of a slice of the piece, and then the width, dx, of the slice. And then we've also got to include the distance as a part of this calculation as well. And so the distance you travel might depend on what slice you're looking at. And the point is, all of that's involved in lifting objects. This would be the integral that we would want to use. And then finally, there's a third type, which is combinations of type 1 and 2. And so we're going to look in the videos ahead at a couple of different examples of each of these types and look at sort of how to approach them and come up with the different values that we're going to need in order to solve them. But mainly there's two formulas here that you need to take away from this. One is the basic structure of the work integral, and the other is what we think of the work integral as being in the case where we're lifting. Now, I also want you to know that lifting implies one of the significant applications of lifting is what's called pumping. So if we look at the work required to pump water out of a tank or oil out of a derrick or anything that we're looking at where there's a certain amount of lifting of an object out of a tank or anything like that, we call those pumping problems. And those particular problems also use this lifting integral. All right, thank you for watching.